The UK study that came out last year, their numbers are on the order of, we'll say, about $10 billion to get the first watt on the ground and have something reasonable happening. We think we can get a significant improvement over that. And it's well within the realm that'd be cheaper than a car program, well within the realm of what it would take to, like the startups you see in the EV realm, to be able to get watts on the ground and start becoming a self-financing entity. And we think we've got the partnerships and all in place that once power's on the ground, it can be delivered in a way that's going to be economic.
From the Defense and Aerospace Report, this is The Downlink, a podcast about the intersection of space, the space business, and defense. Not just what's over the horizon, but what's happening above it. I'm your host, Laura Winter. Hello, and welcome back. At the time of this recording, NASA announced its team is going to make a second attempt at launching the SLS, or Space Launch System. The mission is called Artemis 1. It's a 42-day test to see how well the Super Heavy rocket works, and if this system can get the human-rated Orion capsule a wee bit beyond the moon and then back to Earth. No one is on board this test mission. But if it's successful, astronauts will be on the Artemis 2 mission, and that test will hopefully happen in 2024. All of these tests are geared to open up a new age of human space exploration. What you're hearing now is a test of a different kind from a U.S. company that's hoping to open up a new age in renewable energy production.
All right, so we're live.
Okay, 2 watt first.
They're sending electricity across their laboratory wirelessly.
0 amps on the gate, that's good. Should be 20 volts, 0
Yep,
amps on the drain.
this is the unplanned part 3 of space-based solar power. A couple weeks ago, I had to set aside this episode because of the news. That news was about the European Space Agency pursuing space-based solar power, or SBSP, for Europe. By contrast, here in the United States, the only SBSP program the U.S. government is pursuing, and I'm not talking about a report, is the Air Force Research Laboratory's Space Solar Power Incremental Demonstrations and Research Program. And that's all well and good, but the focus is on providing power to the military at forward deployed locations. That doesn't really address securing nation-level or even city-level energy supply. So that leaves us with the commercial sector. And there are a number of American companies that are aiming to be space-to-ground electricity providers, which, who knows, could shake out to be a more efficient and cost-conscious way to achieve SBSP.
We have a lot more power coming through.
If indeed it's possible. This episode is about the journey of one former General Motors electrical engineer who is now the co-founder and chief technology officer at Virtus Solis.
5 meters, no problem.
All right,
Now,
I'm happy.
Ed Tate. If you need the basics on space-based solar power, please listen to part 1. I'll leave a link to it in the show notes. Now, here's our discussion. Hello, Ed. It's great to finally have you on the podcast.
Well, thanks a lot, Laura. Very good to get a chance to join and looking forward to the discussion we're going to have today.
You know, while I've had the privilege of getting to know you online and through phone calls where you've been really patient in explaining space-based solar power to me, I'd like the audience to get to know you. So take this moment and introduce yourself, Virtus Solis, and where the company is and what you do there.
All righty. Well, this is actually the third industry I've had a chance to work in. I started off as a teenager working in the auto industry. Spent most of my first 20 years as a professional working in General Motors. My first car program I got a chance to work on was actually the EV1, and the last one I had, I'm very proud to say, was a Chevy Volt. From that, I had the experience to start asking the question of how quickly can you actually develop things. In the time that I was in the auto industry, I watched development schedules just collapse. I mean, massively. I watched teams shrink. I watched the development schedules collapse. So I asked the question of how fast can this happen? And that led me to working in the simulation industry as a second leg of my career. Spent about 10 years in the simulation industry. Started initially with a pre-IPO company that was selling called Exa Corporation that sold a simulation that could replace wind tunnels. And we were able to actually help automakers get rid of prototypes, get rid of the need for expensive testing. And they were able to build on this. We were acquired by Dassault Systems, had a chance to work across all industries. That got me into aerospace. And along the way, I'd kept in touch with one of the gentlemen I met at General Motors, John Bucknell. He had a chance to walk through space with SpaceX, go through additive manufacturing with Divergent, and had a lot of ideas on where he wanted to head. We collaborated over a period of time where he bounced ideas off me, and I ended up deciding that the ideas he had made sense and joined Virtus Solis as the CTO. So today we are working on taking the idea of space-based solar, de-risking it, being able to demonstrate that things have really changed from the ideas that were looked at decades ago, and bringing it to something that'll be a reality in the next couple of years, hopefully.
And where's the company based?
We're based, our home office we're virtual, first of all. Our home office is out of Southeast Michigan, and we have physical labs in Indianapolis, but we have people all the way from Europe to the West Coast of the US that are part of our extended team that's developing our technologies.
I'd asked you to come on the downlink to talk about space-based solar power, the state of the technology here in the United States, the market viability, where Virtus Solis is in its journey. But your professional evolution, what you focused on, has always seemed to be more than a few years ahead of the curve. You were working on electric vehicles way before it was cool, years before Elon Musk founded Tesla. How did you get started on this path?
Well, I was very fortunate. Actually, at 17, at one point in time, GM used to actually run its own college. And part of that was that they had the students that went to this college would also do co-oping. And I kind of stumbled upon it when I was in high school, decided I wanted to actually work more than I wanted to study. Kind of funny for a guy that's got a master's and a PhD, but I actually wanted to get started right away, and they were willing to take me in at 17 as a co-op. So I had a chance to work with the electronics division of GM. A lot of people don't realize how vertically integrated the car companies used to be. GM actually had a semiconductor fab in Kokomo, Indiana. I worked out of there. When I went full time, I had the opportunity to fill in for a guy that didn't want to move to Southeast Michigan. And so I moved from Indiana up to Michigan and got a chance to work on the EV1 program. And then over the next decade, I was kind of the youngest guy on the team, and I had a chance to fill in for a lot of odd areas, of which batteries were the one that, quite surprisingly, nobody really wanted to spend much time with. So I got to spend a lot of time on batteries. Along the way, I actually got my master's out of Stanford and made a couple of serious, significant contributions, I think, to improving battery performance at GM.
And just to be clear, when you mentioned the EV1, what is the EV1? Yes, E is electric, V is vehicle, one is, one. But really, what was it?
That was a lot of people will put it down as the first production electric vehicle that really showed you could make a decent car with an electric vehicle. It was fun to drive. Had good acceleration, got 100 miles of range, and that was really, it filled in the first check boxes. And it was tough to do. That vehicle was based on having lead acid batteries when it first came out. So you can imagine lithium ion as generations beyond lead acid, but with lead acid batteries, you're talking about 1980s controls and silicon and things like that were in it. It was able to get 100 miles of range, provide a comfortable driving experience, and it was really the first modern EV that came out.
Now, and when was this? Was this like what? The
96 it came in. It was made available for lease, and then the program wrapped up right around 2000 or so.
And then there's the detour. You worked on aerodynamic, aeroacoustic, and thermal management solutions. I'm not even going to attempt to explain computational fluid dynamics or lattice Boltzmann-based physics. I'm not even sure if I'm saying these things correctly. I am very interested, however, to know if this professional experience led you closer to space solar power.
Yeah, it did. It all contributed to it. It's not a direct path. I mean, the first step I had taken in my career was seeing how to build these complex physical systems. And I can literally say the first day that I started working on car programs, I remember walking in and guys were still using drafting tables. And by the time it was in production, it had been completely replaced by CAD systems. And that revolution of taking something from being on paper, from being literally built out of cardboard, sheet metal, et cetera, to mock it up, to being in a digital domain, means that you were then able to get rid of things that used to take very, very long, like building prototypes, very, very expensive, like shipping prototype cars to the tops of mountains, to Death Valley, depths of winter, you had to do testing, and replace it by simulation. And the first simulations weren't that great, but the question was there. You could see it being this starting kernel of being able to convert from this, multi-billion-dollar testing facility, development program, et cetera, into something that could be done on an engineer's desktop. So I reached a certain point in my career, ended up having EXA recruit me, talk to them. I found out what their vision was, and their vision was a prototypeless, physical testless development and release of vehicles. And I thought that was a very compelling vision. And they had done the first steps towards getting all of this to work when I had a chance to join. Over time, I ended up leading a team that was focused on automotive applications. And then we were able to help different automakers go from a build a prototype, test it in a wind tunnel, build a prototype, test it in cold weather, test it in hot weather, test it on the track to see how it sounded, and replace that completely with a virtual development thing. A lot of great guys were working on this. It was years of experience was brought into it. But the big punchline that came out of it was that it was really possible with the state of the art, with high performance computing, with the right simulation software, to be able to bypass all the things that were massive capital barriers to anybody else entering the auto space. And I do believe that the work that was done in simulation, and eventually EXA got rolled into Dassault Systems. Dassault System has a complete portfolio. They're one of several big suppliers that compete in this area, that it's possible as a startup to come in and lease the software, lease the solutions that let you replace having access to these very expensive test facilities and prototypes. And I think that's helped a lot of the EV makers come up. Now, you ask, how does that get back to space? Well, space, you need very, very tough environments. You got to test it. You've got radiation, you got vacuum, you've got vibration. And it gets asked a couple of times. It's like, that's such a tough environment. How do you make something work there? And it's like, well, I run something under the hood of a car with an engine. I have to run electronics literally bolted onto an engine. 20 years, high vibration, mud, water, boiling temperatures, and you can still make this stuff work. Space is a slightly different environment. The physics are well understood. The simulations can be put together. And then if you focus on doing these things with a very smart testing program, you in theory should be able to pull all your schedules down. So it was a great way to take what I had learned in this environment and move it forward into another one and see if we could apply that to solving some real world significant problems. And the space-based solar addresses an awful lot of the problems we have in the energy markets today, and we're facing overall with resources and prosperity.
So then what happened? I mean, how did you get from Dassault Systems and Simula to Virtus Solis?
Well, John and I kept in touch. We met about 15 years ago, and he had worked through a couple of different ideas on what he'd like to try. Eventually, he settled on, what is the one thing that, for what he'd like to do, he's an aerospace engineer. I'm actually an electrical engineer and systems engineer. I like building big things. I like building things that are challenging, that have high value. And he said, the biggest thing we need to solve is actually energy. Having come from the auto industry again, auto industry is probably one of the biggest consumer products you'll own that just consumes energy. You got your home, which consumes HVAC, but your car is really it. And mobility really does improve lifestyle and prosperity. So it's quite obvious we've got resource constraints coming up. I mean, about 1 billion people in the world don't even have access to electricity. It's less than that, but I mean, it's around that kind of a number. And making energy cheaper, more accessible, and cleaner is a necessary thing to get universal prosperity in place. So how do you make that happen? Everything we have on the path right now terrestrially has some major downsides. Either it has resource limitations such as fossil fuels, it has potential long-term consequences like nuclear, or it's intermittent like wind or terrestrial solar. I mean, terrestrial solar, when the sun's down, you're not getting anything. The wind cannot blow for days on end and potentially weeks on, or not weeks on end, but many, many days on end. And if those systems don't produce, you've got to go back to something else, or you have to turn stuff off. So terrestrial power's got the issue of needing to try to move power when it's needed, where it's needed. And that's major changes needed to clean it up and decarbonize the grid. Space-based solar can economically approach that. My first reaction when John approached me was, this is worth doing. I said, yeah, it's absolutely worth doing. He said, it can be done. And I'm like, I'm not so sure about that. one of the reactions we get is that's sci-fi. It's like, okay, yeah, that's science fiction with a big emphasis on fiction was actually my first reaction is you can't make the physics, the economics, the engineering, and the financing all work out. And, especially with the NASA study from the 80s, it's like, no, the numbers are too big. There's a recent study that came out last year by Fraser Nash in the UK. They put the number still up in the billions. After working a pencil for a long time, having some very good advisors help out, we've actually been able to push that number to something we think is well within the grasp of a startup, well within numbers that can be raised through the kind of financing we can get in a startup. And we've got strategic partner now that is ready once we make the basic technology work to get it out on the grid. So we think that we've got all the pieces that this can happen. And so that's how it all came together.
You mentioned numbers there. What kind of numbers are we talking about?
Well, okay.
To get this
so
done,
I'm going to put it in terms of other things. I don't want to get into exact numbers on the investment, but Fraser Nash with the UK has kind of verbally said they're willing to put well north of $10 billion into developing space-based solar, and it's very much a UK-centric solution they seem to be focused on right now. If you change the parameters a bit, you change what you're trying to accomplish, we think that can be much lower. So, for example, in 1980, if you put it in today's dollars, it's about $1 trillion to do what NASA proposed using their budget numbers from the early 80s. And it's about 20 years from the very first start of the program till the first watt hits the ground. The UK study that came out last year, their numbers are on the order of, we'll say, about $10 billion to get the first watt on the ground and have something reasonable happen. We think we can get a significant improvement over that. And it's well within the realm that'd be cheaper than a car program, well within the realm of what it would take to, like the startups you see in the EV realm, to be able to get watts on the ground and start becoming a self-financing entity. And we think we've got the partnerships and all in place that once power's on the ground, it can be delivered in a way that's going to be economic. Now, the other piece that's there that really changes this is launch costs have dropped dramatically. I mean, we have to recognize that SpaceX has done an incredible job on dropping the launch costs, but they've done more than just the fact that they can do it cheaper. I think they've highlighted to a host of other launch startups, and I think right now there's more than 100 of them, that it is possible to do reusable launch. It is possible to drive that cost down. And so those pieces being in place look like they're absolutely necessary to then make everything else come along and be economic.
Virtus Solis was founded almost 3 years ago now. And the claim is that it is, quote, the first low cost space solar power system. Describe what really is making that lower cost. And you also say, at least on your website, that there's an $8 trillion market that you're entering. So take us through that business case.
Okay. So let's start off about what's involved in space solar power. There's really three major costs you have to deal with. First one is, and this is when everybody focuses on, I got to put a satellite up that's able to convert sunlight into energy I can get down to the earth. And that can be microwaves, that can be lasers. We've adopted what we think is a nice compromise of a frequency we've selected for microwaves. Then you've got the cost of getting it into orbit. And then finally, you have the cost of putting something on the ground that receives it. Where you put an orbit has a massive impact on your cost. It's like the cheapest is like a low Earth orbit. One of the more expensive ones is hitting GEO, and then there's orbits that are in between that. So we've chosen kind of the Goldilocks solution, and we have a choice of using Molniya orbits that are a nice compromise between giving us a long visibility of our customers and having cheap entry and insertion into orbit. That helps us manage our launch costs. For the satellite, we've looked at a lot of the proposals. If you look through the history of proposals, the NASA one from the 80s, once again, is beautiful. It's like they're manufacturing girders in space. They've got habitats. They're going to, mine asteroids and everything else. And it's really incredibly comprehensive vision. The Fraser Nash study looks at a little bit simpler design. Everything's assembled on Earth, basically brought up, or everything's manufactured on Earth, brought up and assembled. We're taking it even simpler and looking at turning this from being a gigantic civil works project in space to being a ground-based, high-volume manufacturing problem with very simple assembly in space, very simple management. And our choice of mission, our choice of devices, our approach to doing one scalable part that's produced in high volumes all play into driving these costs down. There's a usual thing that shows up in industry, which every time I double production volumes, I usually get some, you can use, double or increase by a factor of 10. But every time I increase production by some order, I'm going to get an appropriate decrease in cost. And coming from automotive, what I'm used to thinking in terms of is what is the raw material cost I need? What's my markup for all the pieces I'm going to sell? And that's giving you how to build your pricing models. Aerospace is very different. Actually, I'll go back to the EV1 example. I remember one of the first encounters I had with an engineer from Hughes Aircraft, and bright-eyed engineer hopping through the site at Hughes. I had a chance to meet a guy that was working on radars, high-power microwave systems. And I was sitting here talking about it, and saying, it does this, it does that. It's got all these neat features. I've been working on it for 15 years. I said, wow. I said, how many do you have in production? And he looked at me and he goes, this is it. So there's a very different attitude you got between the low volume craft, high performance aerospace, and just figure out what you need and produce it in incredibly high volumes that drive the price down. So high volume, simplification, and the right choice of mission, orbit, and overall system design, we think we can drop that price down dramatically.
Just to be clear, when you're saying high volume, are you talking about putting up many satellites?
Yeah, we're talking about we're talking about thousands to get started. So, but let's explain what we mean by terms to be very clear. We have a fundamental building block that's on the order of about a meter and a half, which we're calling a satellite. And it's a very stripped down, simplified system that's going to convert solar into RF. These are then assembled into what would be an array. So one structure with a lot of satellites that are all linked together in an array. And that in turn provides the energy that comes down in a structured form to hit a receiver on the ground. So we're looking at thousands of satellites being put into initially one array, then being put into what's called a constellation, which would be 3 arrays that are physically separate in separate orbits. But the 3 satellites would then coordinate and work together to provide continuous ground coverage for power on 2 different sides of the planet. So another thing that we're looking at, the national programs all tend to be focused on provide power to one nation in one location, and that drives the mission thereafter. We're looking at it in terms of we think the right solution is the lowest cost to get this started. The lowest cost means you're going to be an international power provider, and that it's very out of necessity going to be providing power to multiple customers in multiple locations that are politically separate.
And just so that I clearly see this in my mind and that my audience does, with these smaller satellites that come together in an array, you're talking about, when they get up into orbit, that they would essentially link up together.
Well, we'd be looking at doing assembly in space. So the idea is, there have been proposals like I've seen proposals for things like self-navigating satellites, and they'll link together and all that. Once again, it's simplicity. These can be very, very simple. The assembly process can be quite simple. And the idea is that we will ship them up in batches. There'll be some dedicated hardware that actually does the assembly process to go from one satellite to an array of 2, then 4, then 8, and keeps expanding outwards. And as we do that, it's a simple fastening operation. So we actually have a research project going on right now to drive the cost on that down to the minimum. But I see it as simply as like a manufacturing operation of a plant. You don't have to do a lot of really fancy things to install a screw. You have some appropriately built automation, and we look at it as I'm just assembling these arrays. They link them together. You move on and do the next one, and you have to have enough facilities to handle anything that goes wrong during the manufacturing or the assembly process.
This has a lot of moving parts: technology development, launch, the on-orbit manufacturing that you just explained, ground real estate, distribution. Are you partnering, and how are you partnering? How are you going to get this done?
So right now we have a strategic partnership with Intersect Power. So Intersect Power is like one of the largest solar installers in the U.S. They're putting in energy storage and energy production with solar on the order of gigawatts. We've got their CEO is actually one of our lead investors, and this is what he sees, and he's investing in us because he sees it's possible and it's the right thing to do to move renewables forward. So with that, we've got a partner that can help cover what needs to happen on the ground. By working appropriately with the folks that are already doing renewable, they know how to get the permitting, they know how to take care of getting the energy into the grid. And it's just really, at the end of the day, receiving RF versus receiving solar is a different piece of hardware, some different configuration options. Then we have launch. There's an entire ecosystem around launch. So we look at going to one of the existing suppliers, and there's lead times and things like that that be worked out, but we see as a path to be able to get the launch at the cost we need going to the existing ecosystem. So that leaves us with the new technology development. Wireless power is the highest risk that we see. And part of it is just simply nobody's demonstrated really doing wireless power at the scale that we need to. And it's really hard to do on the ground. That's the problem is if you look at it for trying to use it for terrestrial power, you have to choose frequencies that help you shrink things down. When you choose those frequencies, you have issues with rain, you have issues with weather, and the right frequency for us to choose based on spectrum allocation, based on orbits, based on the scale we can work at, means that I really can't just stand up a transmitter on one side of a mountain and go to another mountain and stand up a receiver. So we have to do one very heavy simulation, and we're working on getting to the point that we can simulate the full scale down to every antenna that's in the system. We have to validate that against what we're doing. We have other simulation to validate the structures and things like that. But then we have ground-based demos that we're focusing on right now that will allow us to show that one is we know how to design this, we know how to coordinate it, and it scales and does exactly how we expect, which eventually moves from ground to low Earth orbit to a minimum value demonstration that's actually producing revenue, providing power to somebody on the ground.
You know, you're going to run into headwinds from the traditional energy producers. I dare I say it, but it's well documented that they're pouring millions of dollars, probably more, into lobbying for the primacy and the preservation of what's essentially a 19th century technology. How are you going to be able to make that end run to reach industries that rely on electricity and American homes?
Well, I mean, first off, and actually, this was one of the things that when I joined, I wanted to join something that was going to decrease cost. So as we built up the models, there was an awful lot that was involved in proving that there is a path to get to lower cost electricity. And so when we say we're going to be a low cost electricity provider, I mean, that's the focus that we have on providing that. And the numbers work out with launch costs that are coming up, plus the electronics cost and other pieces that we have there. Now, you're asking kind of about entrenched interests that are out there. It's like, I think the legislation's already in place and the demand from the population's in place that's driving down caps on the amount of carbon you're going to be allowed to emit. And there's bottlenecks that are showing up in the fossil fuel supplies and things like that that I think are making people far more open to looking at alternatives. The challenge you've got right now is existing terrestrial renewables are all, for the most part, intermittent or they don't scale well. Like I can't put geothermal everywhere. I can't put dams everywhere, which are the two that can provide firm, clean, renewable energy. Those are limited resources that can go a little bit. And when you push too much renewables into the grid, the problem is you now have to start looking at connecting grids at a continental scale, or I have to start putting increasing amounts of energy storage on, and I have to look at doing spot pricing plus other demand management, including things like asking industries potentially shut down for a few days, affecting their bottom line tremendously just to get that energy back into the grid to meet necessary services. So we think the combination of what's happening legislatively, increasing costs for fossil fuels that are showing up in the market, plus the challenges with renewables mean that we can come in and as space-based solar, we compete against, energy generation, energy storage, and energy transmission. And we're actually a very nice, neat solution to put the power where it's needed, when it's needed, and address the bottlenecks that are showing up right now.
I'd also imagine that some of the affordability that this would create is the fact that we wouldn't really need batteries per se or that much storage because this power source is virtually 24/7. I mean, maybe, 23 and 45 minutes, 7, but you know what I'm saying.
Yep.
What kind of savings would we be talking about when we're talking about storage?
Okay, well, for example, there's a study I found from like 2018 that was looking at New York as a power market and Texas as a power market. And, what they're looking at is you try to push your carbon intensity of your electric grid down. There's almost an increase in the cost that you're going to be looking at as an end user of that electricity. And that cost is showing up because you're having to invest in more transmission lines. You're having to invest in more real estate being converted into renewables. You're looking at storage, and actually starts becoming a very big thing is just trying to get the storage. And it's actually compounded because like the Southwest in the US is actually an ideal market for, say, solar. I can put a couple of hours of energy storage on. I got wind, and I can supplement with some peaking power plants. When I start looking at northeastern states like New York, the New England area, and I live in Michigan, so Michigan actually has, because of clouds, we have one of the worst ratio of like peak summer to peak winter solar that we have in the U.S. But the funny thing is, most people think of the U.S. and Europe, say, being about even, and Europe, Germany, and the U.K. especially are farther north and have even bigger seasonal variations. So there's going to be the introduction of a couple of hours storage, which will start taking care of, the first step of decrease in carbon intensity in the grid. But when you start going further, you have to start looking at like seasonal storage potentially. And this is a place where space solar really comes in. It can fill in for those seasonal gaps, provide the base load that you need, or the term is firm, clean, renewable energy that would be needed to keep the grid stable and provide energy when you need it, where you need it, which in the middle of winter, if you're trying to decarbonize, you're going to need it for heating. You're going to need it for all the other things, the additional lighting loads you're going to have in winter.
So when is this coming to my electrical plug?
Well, that always depends on a lot of things. If everything lined up, this is something that can be demonstrated and have watts on the ground in a couple of years. Now, obviously, a small startup, you've got things that you are going to show up along the way, and there's risks that you'll take in getting there. But the competing national teams that are looking at it are all talking about being able to get power on the ground by the end of the decade. And that's probably going to be small scale demos. We're working on a little bit more aggressive schedule than they are, and you're talking about by 2040 potential that being a significant player in baseload. You're also looking at once it's demonstrated, I think it's going to scale very well. So the money has to flow into producing new generation capability, transmission capability, storage. Once it's demonstrated, I think it's one of those things that will start drawing even more investment in and grow very quickly after the first demos. And space is big. There's a lot of room up there for a lot of different solutions. And so we see that, just like you don't have one power plant provider today, there's probably going to be an ecosystem of providers as time goes on. But first one that gets there, I think, has an awful lot to gain, and we'd like to be the first there.
Ed, thank you so much for making the time to speak with me. This was fascinating.
Well, it's been a pleasure. I appreciate the chance to have a discussion with you and share some of the stuff that we're doing today.
That's it for this week. If you like what you're hearing, follow the downlink on Twitter and subscribe to the podcast on your favorite podcast platform. For the latest defense news and analysis, listen to the Daily Defense and Aerospace Report podcast hosted by Vago Muradian, and listen to Cavis Ships to hear the latest on what's happening in the maritime domain. I'm Laura Winter, and thank you for listening.